Okay, so today we're going to talk about the math that's involved with acids and bases. So we've already talked about the Arrhenius definition of acids, where acids can generate hydronium ions. Those hydronium ions can be measured. So the concentration of hydronium ions is written like this. Sometimes we write it as just H+. Either way, this is the concentration of hydronium ions. That concentration is what we use to determine the pH. Okay? When we want to talk about pOH, we're talking about the concentration of hydroxide ions. So for bases, what we measure directly is the concentration of hydroxide. And that's what pH and pOH is all about. So we're going to start by talking about where it comes from. And really, the key to everything is water. When two water molecules are near each other, they can break up into H3O plus hydronium and OH minus hydroxide. And like all reversible reactions, there's an equilibrium constant. The equilibrium constant for the dissociation of water is 1.0 times 10 to the negative 14. Why is that important? Well, you guys have all seen this 14 before. Many of you have said that the pH scale goes from 1 to 14, and that's really keeping that 14 in mind. So a way of doing this, since water is liquid, and the ions are aqueous, the way we write this, pure liquids do not get taken into account in the equilibrium constant. So K water is just the concentration of hydronium ions times the concentration of hydroxide ions. And like we said, that equals 10 to the minus 14. So what we're going to do is a math function, the negative log. Negative log is represented as P in math class. So if I take the negative log of water, 1.0 times 10 to the minus 14 equals H3O plus times OH minus. What you may remember from math class is that when you are multiplying logs, what you do is add together. When you're multiplying things, you add together the logs. When you're dividing things, you subtract logs. So if I do negative log of 1.0 times 10 to the minus 14, that's equal to pH plus pOH. And as it turns out, log is the math thing for the inverse of raising 10 to a power. So the negative log of 1 times 10 to the negative 14 happens to be 14. So this is an equation that I need you to remember. pH plus pOH is always going to add up to 14. Okay? When it's neutral, right, the hydrogen and hydroxide are equal to each other and balanced out, that means pH of 7 plus a pOH of 7 equals 14. That is why 7 is neutral on the pH scale. So how are we going to use this? Well, we've already said P means negative log. That means that pH is just the negative log of the hydronium concentration. So if you know the concentration of hydronium ions in solution, you can calculate the pH just using your calculator. So how do we find out the concentration? The simple way is to take the number of hydrogens in the formula for the acid and multiply it times the molarity of the acid. So for example, if I have a 0.5 molar solution of sulfuric acid, remember SO4 sulfate becomes sulfuric acid, okay? The the concentration of hydronium ions is equal to 2 hydrogens, right here, times the molarity, 0.5. So if we do that, it equals 1. Okay? So the hydronium concentration is 1. So what is the pH? pH is the negative log of 1. As it turns out, the negative log of 1 is 0. So the pH of that solution is 0. So whenever we have an acid, it's really easy to do the pH. Same thing with a base. We can do the pOH. pOH is the negative log of the hydroxide concentration. And we get the hydroxide concentration the same way we would have gotten the hydronium concentration. So let's say I have calcium hydroxide. And this time my solution is 0.002 molar. So first I find the hydroxide concentration. And that's 2 hydroxides times my concentration, 0.02 molar. Sorry, that should be 0.005. The reason I'm changing it is that I don't have to use a calculator to find the log. Okay, so what do I get there? I get equals 0.01 molar. Okay, that's my concentration. So negative log 0.01. Same thing as saying negative log of 1 times 10 to the negative second. And that's 2. So my pOH is equal to 2. So how am I doing this log in my head? Well, here's the nice thing. On the SOL, they're always going to give you something that is 1 times 10 to a power. So to find the log, on the new page, to find the log of anything, we first write the number in scientific notation. Next thing we do is get rid of everything except the exponent. This only works if it is 1.0 times 10 to some power. If you have 2.0 times 10 to a power, you're going to have to use your calculator to calculate the log. Right. In order to find pH or pOH, change the sign on the exponent. So I'm going to ask you to take a second to find the pH of a solution of acid. And I'm going to ask you to do a 0.001 molar solution of HCl. Take a second, pause the video, and figure out the pH. Okay, so how are we going to do this? We start by finding the concentration of hydronium, which is 1 hydrogen times the concentration. So I get 0.001 molar. I write my answer in scientific notation. 1.0 times 10 to the negative third. Then I use the exponent only. That's a -3. And since I'm trying to find the pH, I have to change the sign. So the pH is equal to 3. Nice and simple. And this works for any strong acid or to find the pOH of any strong base. There is one other thing that we need to be able to do, and that is to figure out how to get the pH or pOH for a weak acid or a weak base. So for weak acids and bases, the only difference is we have to multiply the concentration of hydronium or hydroxide by the percent dissociation. So the concentration of hydronium ions is equal to the percent as a decimal times the number of H's times the molarity. And then the problem is the same as it was before. Remember I told you, back up here, pH plus pOH equals 14. How are we going to use that? Well, how often have you guys heard of using pOH? My bet is none of you have ever heard of it before. Everybody knows about pH for acids and pH for bases. Nobody really talks about the pOH of things. So how am I going to find the pH of a base solution? So let's try finding the pH of a, we'll go with a 0.0005 molar solution of magnesium hydroxide, which is a weak base, and it dissociates about 10%. So the first thing I'm going to do is find the concentration of hydroxide. I'm looking for pH, but I'm given hydroxide. So I can only find the concentration of hydroxide. I don't have hydrogens here. So the concentration of hydroxide is equal to 0.10, that's my 10% dissociation as a decimal, times 2 hydroxides from my formula for magnesium hydroxide, times the concentration 0.0005 molar. And when I do that, I get 0.0001 molar as a concentration of hydroxide ions. Like before, I can now find my pOH. I'm using hydroxide concentration. That means pOH. I can't find pH directly. So to find my pOH, I write my concentration in scientific notation, 1.0 times 10 to the negative fourth. I use the exponent, and I change the sign. So the pOH is equal to 4. The problem is I wasn't asked pOH, I was asked to find the pH. So I use my equation. pH plus pOH always equals 14. So I know my pOH is 4. X plus 4 equals 14. That means the pH of my base equals 10. And that makes sense because it's a base and the pH is higher than 7. The only other math you would be expected to do with acids and bases is titration. Titration is a lab procedure. And we use it to find the concentration of an unknown. And we do that by neutralizing it. So we'll use an indicator to tell us when we've reached the end point, when the concentration of hydrogen and concentration of hydroxide are equal. And the one we use most often is called phenolphthalein. What you need to know about phenolphthalein, it is pink in base, and it's clear in acid. So if you start with a base, you have a pink solution, and you drip acid into it 1 drop at a time until it just barely stays turned clear. If you start with an acid, you start with a clear solution, and you drip base into it 1 drop at a time until it just barely stays pink. And in order to find the concentration, we use an equation that you've actually used before. We did this back in solutions, the dilution equation. The molarity of the acid times the volume of the acid is equal to the molarity of the base times the volume of the base. So when you do the experiment, you know the volume of your unknown, you know the molarity of whatever your known solution that you're using to titrate with. In the experiment, you find the volume that you're using to titrate with, and so you have 3 of the 4, and you can use that to calculate the molarity or concentration of the acid. So this is really just MAVA equals MBBB all over again.